Section 2.5 is called the chain rule. This is probably one of the most important rules. This is kind of an extension of the power rule. But between the power rule and the chain rule, again, which is just an extension of the power rule, those are, to me, the two most important derivative rules that you need to know. So this is an extremely, extremely important rule that we will be using numerous times, virtually every time, for the rest of the semester. Okay, so let's look at it. It says, we have seen to solve problems like the derivative with respect to x of 2x plus 1 quantity squared by expanding 2x plus 1 squared to 2x plus 1 times 2x plus 1, which equaled 4x squared plus 4x plus 1, so that's if you did foiling, and then you take the derivative of the expanded form. In the last section, we learned that you could have done 2x plus 1 times 2x plus 1. You could have used the product rule. But what if we wanted to find the derivative with respect to x of 2x plus 1 to the 45th power? Can you imagine foiling that out? Having 45 individual factors, having to FOIL that out? This problem would take forever. It would take pages and pages of math, and it would take absolutely forever to figure out. So how can we do it when it's not just one thing raised to the 45th power, when there's multiple things? For instance, let's look at this. What if I found the derivative with respect to x of x to the 45th power? Well, that's easy enough because it would just be 45x to the 44th power. Drop the power, keep x, and bring it to the power minus 1. So if it's just an x in there, we've got it. We can do this. But what happens the second that it's no longer x? Does that truly change the derivative that much? And the answer is both yes and no. So how does it change it? I'm going to show you something it's called the chain rule. It says let y equal f of u. This is where we kind of get into compositions of functions. And that's why I had you look at the compositions of functions in your lines and functions review. It says let if y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x, the composition of the two functions, is differentiable function of x, and dy dx equals dy du dx. Well, mathematically that's not hard, because dy du times du dx, well, the du's, those would simply cancel, and you would just have dy dx. So mathematically, a very simple concept, very easy. We've just kind of expanded it. But conceptually, what the heck are we doing? And this is where we call u substitution. So what does this mean? This means two parts to me. The first part here is find the derivative like you would. If it was just x. Don't mess with the inside. The second part here is multiply times the derivative of the inside. So dy du is finding the derivative of the original function just like it was x. So we had 2x plus 1 raised to the 45th. You would treat it just like it's x to the 45th, which would be 45x to the 44th. You treat it just like it's x, but you don't mess with the inside. But then the new part is that you have to multiply it times the derivative of the inside. So that's what this is. That's what the chain rule is. Find the derivative of the outside, keep the inside the same, and then multiply that times the derivative of the inside. We're going to do numerous examples of this. I mean, I can't tell you how many examples you're going to be doing, but here's the process that I wrote up. It says define u. U is usually the inside of the function, or the inside of the parentheses underneath the radical, etc. Then you're going to find u prime, which is the derivative of u with respect to x. Rewrite the original functions in terms of u and differentiate. Then the chain rule says we must multiply by u prime. Biggest thing here is do not forget to multiply by the derivative of the inside. Do not forget to multiply by the inside. Then it says back substitute for u and simplify if possible. Okay, so let's start this out by doing the baby one, the 2x plus 1 squared. We know we could expand this. We know what the derivative already is. We found that out in the opening paragraph. Well, the derivative, it turns into 4x squared plus 4x plus 1. So the derivative should be 8x plus 4. How could we get this? Well, if you look here, we have something raised to the second power. And what is that something? I'm going to write 2x plus 1. I'm going to write that in red. And so what the idea is the 2x plus 1, because it's more than one thing, that's what makes it difficult. That's what we let u be. U is the inside of the parentheses. U is the ux plus 1. So then we want to find the derivative of u with respect to x. Well, what's the derivative of 2x plus 1? Derivative of 2x would be 2 times 1, which is just 2. And the derivative of 1 is 0. So the derivative of 2x plus 1 is simply just 2. So this is our function y, or they called it f of x. It doesn't really matter. But let's look at y in terms of u now. So instead of 2x plus 1 quantity squared, would you agree that's really u squared? That's called the u substitution there. That's really u squared. So what's the idea now? We find the derivative of y with respect to u. So the derivative of y with respect to u would be, well, what's the derivative of u squared? It's 2u to the first power. Okay, so what does the chain rule officially say? The chain rule officially says to find the derivative of the original function with respect to x, you find the derivative of y with respect to u, and then you multiply that times the derivative of u with respect to x. dy du, du dx. Well, we have both of these things already. We have dy du right here, and we have du dx right here. So let's plug those in. The derivative of the original function would be dy du, which is 2u, times du dx, which is just a 2. So I'm getting that the derivative, which is dy dx, I just wrote y prime though, would be 4u. Now we just back substitute for u. Well, what was u? U in the original problem was 2x plus 1. So that'd be 4 times 2x plus 1, which we could expand this if we want. That's perfectly fine right there. Or you could distribute it. That would be the 8x plus 4. And that's what we noticed that the derivative would be of 4x squared plus 4x plus 1. The expanded form of it was 8x plus 4. So that's the official way of doing u substitution. Make u the inside of the function, find the derivative of u, rewrite y in terms of u, find the derivative of y with respect to u, tack together dy du, du dx. You now have the derivative. You just have to back substitute for y. But I'm telling you, man, it's going to get a lot easier than this. I'm not going to make you do all that substitution in there. I mean, you still need to do u substitution, don't worry. But it does get easier than this. It's not quite so different. Here's what I'd really realize. Here I'd say let u equal 2x plus 1. That's the same. I'm going to call it u prime instead of writing du dx. If you guys are okay with that, I'm just going to write u prime. Remember, it's just different notation. It's the same dang thing. Again, the derivative of 2x plus 1 is 2. And then I'd look at the original problem and I would say y equals u squared. And then that would tell me that the derivative of y would be 2u. But remember, this is supposed to be with respect to x. So anytime it's not with respect to x, it would be times u prime. So in this case, this would be 2 times u, which was 2x plus 1, times the derivative of u, which is just u prime, which is just a 2. And that's where I'm getting my 4 times 2x plus 1, or I could expand that to the 8x plus 4, which would be perfectly fine as well. You're going to get better and better and better at this. You'll get to a point where you're going to see my writing go to something like this. I'm going to say f prime of x is equal to bring down the power, keep the exact same thing, 2x plus 1, to the power minus 1. So that'd be to the first power. So that's treating it just like it was x raised to the 2 power. But then I need to multiply it times the derivative of the inside. So I'm going to write it like this, 2x plus 1, and then I'm going to put a prime there. So this is how I like indicating the chain rule. As I say, look, I take the derivative just like it was before, keeping the inside the same, but then I have to multiply it times the derivative of the inside. Well, the derivative of the inside is just 2, so this would be, at this point in time, 2 times 2 is 4, times 2x plus 1, and I would have been done. So again, this is 3 different ways of doing the same problem. They're all using U substitution. They're all using the chain rule. It's just your level of comfort. The first way that we did it was the true, authentic mathematical way of doing it, which is finding U, finding du dx, rewriting y in terms of u, finding dy du, and then multiplying dy du times du dx. This is the process that you would see in the textbook. This is what they'd do. The pink one, the second process we did, nice quick u substitution. We just wrote y prime instead. We back substituted for u. But man, I'm telling you, after 100 of these, you're going to get so good that you're going to be able to do the third process, which you're going to realize, drop the power, keep the inside the same, the power minus 1. Just remember to multiply by the inside. The problem is if you do it this blue way, this fast way, this quick way, a lot of people forget to multiply times the derivative of the inside. So that's why I tried highlighting numerous times. Never ever forget to multiply that times the derivative of the inside.